Welcome to this webinar session about OECF, noise, dynamic range. In our typical trainings, these topics cover like half day, but I don't want to hold you on the screen for half day about these. So I picked some key topics that I would like to share with you in this session from this context. Okay, so OECF. OECF stands for Optoelectronic Conversion Function, and there is an ISO standard, the 14524, that describes how to measure it. The nice thing is we can combine that measurement with ISO 15739. So actually we measure typically OECF, dynamic range, noise according to SNR or with SNR, and visual noise. It's the same time, so with the same target, same setup. That's of course very powerful and very useful. So OECF, what does it mean? It's basically a function of digital value versus luminance. So we use a test target that provides different luminances to the camera and then check how does this camera reproduce these luminances, or how does the camera convert these luminances into digital values, and that is the OECF function. You can have multiple test targets for that. So there's you can have, it depends on the different number of patches that you have, on the contrast or the dynamic range of the target itself, if it's manufactured in reflective or in transparent. So there are some decisions that you have to make when testing a camera or when choosing a test target for that. So the one important category of test targets is if it is transmissive or if it is reflective. So the reflective chart is like you pin it to the wall and you have light sources illuminating this test target. That is a relatively easy setup, easy to do, but there is no material out there that can create the dynamic range or the contrast that is required for today's cameras with a reflective material. So even high-end absorbing materials will give you a dynamic range of maybe 1,000 to 1, which is 60 dB and not sufficient for most cases these days. So you need to have a transmissive test target. Transmissive test targets are back illuminated, so you need a light source that can do that, so that will be uniform, back illuminates the test target, and then provide different luminances to the camera or to the device under test. So if you, for today's cameras, in most cases, if you want to measure dynamic range and cover the entire range of OECF, so how the camera reproduces luminances, you need a transmissive test target, and you need a powerful light source or a good performance light source behind that is uniform, stable. So for example, the LE7 of image engineering with IQLED technology, or an LG3, so high quality light sources. Something worth to mention here is, even though we talk about the ISO standard, in some cases the test targets that we provide do not fully follow the ISO standard by intention. So the ISO standard is written and designed for consumer cameras with single exposure modes. For that, it is described in the standard how the distribution of luminances or of optical densities of these patches should be. That works well for contrast of 1,000 to 1 or of 10,000 to 1. So 60, 80 dB in this range. If you go much higher, so going like into ranges of 120 dB or even more, you end up with relatively large differences in the last two patches or in the darkest patches. And so you lose measurement accuracy in that part. So that's why it is recommended, if you have cameras that you know have a high dynamic range, so that it's either all devices that will feature multi-exposure so some mobile phones and so on. Or if you have security cameras or like automotive cameras, they will most likely have a very high dynamic range, so their target also needs that. But then we would recommend to use more patches, so like 36 patches, and use a distribution of these patches that does not fully follow the ISO standard. That is, for example, our TE269, and there's the option B or C. In this plot, you can see what the distributions of optical densities that you have. So on the x-axis, you see the number, the patch number. On the y-axis, you see the optical density. So the target in blue line, TE264, according to ISO standard, with a contrast of 1,000,000 to 1. You see that in the last two patches, you have you go from optical density less than 4 to 6. So you make a huge step there. And in all these ranges, you have no measurement position. So your dynamic range measurement might be influenced by that or less accurate. So might not be the best choice for that. Which is the TE269B or C, where we have 36 patches. And then we have made sure that you have enough patches to do a proper measurement. Especially the TE269C is also following an IEC security camera standard, so that you have a linear spacing in dB from and we reach up to 134 dB. So a huge dynamic range of a test target. Which you need in many cameras. So if you have a high performance camera, you need high performance test targets. Simple as that. Okay, I don't want to talk that much about signal to noise ratio. There's the ISO standard, you can measure it, and it is used commonly. But I want to highlight particularly the visual noise, also in the ISO standard, and I think for many applications a very important metric. So what's the problem with SNR? So SNR can or does not correlate that well with the human perception. So even though people say, yeah, you need this certain SNR so that you cannot see noise, this is you have to be careful with these statements. Because it does not, the SNR does not correlate that well. So you can have, or that's our experience in our lab when testing hundreds of cameras, thousands of cameras. You can end up having a camera that has this, or two cameras that have the same SNR but differently show different amount of noise visually, or that they you don't see any difference but you measure a difference in SNR. So that both can happen. And that's because the human observer does not see all the noise that is in the image. And the human observer can see some spatial frequencies better than others. There's a typical, or just try to illustrate this a little bit here. So take these three patterns. So they all three have the same mean value and have the same variance or standard deviation. But of course, you have on the one on the right, you can actually see the pattern, while on the left you can hardly see that. Why is that? Yeah, because the spatial distribution is different. So the pattern is bigger, and therefore you can see it easier. So that just as a very simple way to illustrate that the SNR itself does not just give you any information about how the noise appears, how it looks like. Therefore, it does not give you the number how visually is perceived. For that, you need the visual noise. Visual noise was an informative annex to a previous ISO version, and we at Image Engineering implemented it already in 2007. I mean, it was out there for a while, but we were looking for some new metrics, and yeah, we saw this and we tried it, and we saw since then we use it in our commercial tests. So when we test devices as a service in our test lab, when we need to judge cameras, if VCX does it or any other reliable objective test procedure, we use visual noise. It is now part of the ISO standard, also of a normative part. And maybe just to mention, there are different flavors of visual noise out there. So there is the ISO 15739 visual noise, but also the IEEE 1858, so also known as CPIQ. They defined a procedure to measure visual noise, even though it's called the same and the concept is very, very similar. There are differences. So the CPIQ tried to improve the ISO method. Actually, they never could really show that it is really improved. So, and I personally haven't seen that significant issues with the ISO approach. Therefore, decide for yourself, have a closer look at that. But we at Image Engineering, will follow the ISO standard, and then know there is activities going on, reviewing it, and there might be an upcoming ISO standard that might have changes in that, but the core concept, I think, will remain the same. Okay, how do you describe perception or the human perception? So what we use for that is the so-called contrast sensitivity function, CSF. The ISO standard uses the SCLAB contrast sensitivity function that describes how well you or human observer perceives spatial frequencies. The typical behavior there is that very low spatial frequencies are not perceived that well. Then you have a peak where which you can see very good, and then it just falls off, and that is just limiting by our eye. So very small details we can't see that well anymore. What you can also see in this graph is that we have the achromatic, so the intensity, much higher than the chromatic CSF, which is the color information. Actually, it's nearly double as much spatial frequencies or little details that you can see in the luminance than you can see in the color. That's what, for example, video algorithms or video compression algorithms take advantage of when they just throw away with subsampling half the color information. That's because we can't see it anyway as human observer. Okay, how does it work? So the CSF is, so the amplitude you see, and it is plotted versus cycles per degree. How can I understand cycles per degree? So that's the spatial frequency per viewing angle. So if I have an object, you see there, condition A, I have the object close to my eye. So I have a certain amount of line pairs for a large angle. So I have a low cycles per degree. And so I move in the area where I have the peak, maybe, so where I see the details very good. If I now move the object further away, I have the same number of cycles, but for a smaller amount of degree. So I move on the CSF to the right, so I can see worse. That's a normal thing that you have. You have a sheet, you have some letter, and then you have a look at that close to your eye. You can see very well, and you move further away, you can't see it anymore. So this is exactly what the graphics here, what the CSF tells you. So how does the algorithm work? Let's take, we have the image and we crop a small region of interest, and we want to measure the visual noise in this region of interest. So that starts that we have this RGB image for this small noisy pattern. And then we do a conversion into the XYZ color space, so a device independent color space, and then we go into the so-called opponent space, ACC. And then the core, most important thing of the visual noise measurement happens, and that's the frequency filtering with the CSF. So we have seen the CSF before. So we do here filtering depending on the viewing condition. I always make the comparison to like MP3. If you know how MP3 works, basically MP3 throws everything away that we can't hear anyway. Here we throw away or we suppress everything that we can't see that well. So some pattern that we can't see anyway will not contribute to the noise measurement. And some patterns that are very important or very attractive to our eyes, or we see them very good, they will be boosted, they will be amplified. So that way we have a weighting in there, and according to the human perception. After we did the filtering, we go back into ACC, the filtered ACC, then we go to the filtered XYZ, and then we go into the LUV color space. And there we calculate the visual noise as a weighted sum of the standard deviations in L, U, and V. And there are weighting factors on that, so that at the end you have a single number of visual noise that describes that gives you the noise measurement. And here, other than in SNR, we have the higher the worth. So the higher the visual noise metric is, the more noise we actually have in the image. And by design, we can say that a visual noise value of 1 is about the perceptual limit. So 1 and below, a normal human, an untrained normal human observer will not see any noise. And the higher the number, the more noise you get. So in the range of like a visual noise of 3, 4, you have already very significant noise. If it's 6, 7 or more, you have really heavy noise there. So that's just to give you an idea how the range is. Okay, that's the visual noise I picked, and I want to talk a little bit about dynamic range, or how dynamic range is measured. First of all, also very important, we have to differentiate what dynamic range are we actually talking about. So there is the input referred dynamic range and the output referred dynamic range. The output dynamic range is mainly used or often used by computer scientists, or so that they say, hey, I have a dynamic range of 16-bit. So that means that they can encode values in 16 bits, so that they can create 65,000 different values. That's already quite good, or is an important number, but this is not what we talk about dynamic range in images. In images or cameras, we use the input referred dynamic range. So that is the ratio of the maximum luminance that we can have in a scene compared to the minimum luminance that we can have in a scene. So you see that here. So the isodynamic range is the ratio maximum luminance divided by minimum luminance. The maximum is defined by saturation. So as soon as you reach the saturation, so the maximum of your digital encoding you can have, so in let's say an 8-bit image, it's 255. So as soon as you reach 255 as digital value, you can add more and more light in the scene. You're not capable to capture it. You lose the information. So loss of information as soon as you reach saturation. That's the upper limit. Then we have the lower limit, so the minimum luminance, that is defined by noise. So as soon as you reach a certain signal-to-noise ratio, so you say, okay, if I have less than a signal-to-noise ratio of 1, so where signal and noise is equal, I have a loss of information. So less than that, there is no information left. So the isodynamic range is basically covering that range where you have some form of information at all. It does not really mean that that is everything where you can perceive details very well or where you can see everything. It's really which range do you have loss of information. So that the saturation, that is mainly the sensor saturation. It can also be clipping in the signal processing, so that the signal processor is then clipped, and in the processing somehow it's covered, and you can't get higher than that. The minimum is, typically it's the noise from the sensor. It can also be clipping. So for example, in many applications you have a like black level compensation, so that you say, okay, from the sensor signal I cut off the lower signal because I say that is only noise anyway. So that can also reduce your dynamic range, same as like flare and these aspects that can reduce your dynamic range. So you see in this graphic, so we reach to the right, you have the saturation, to the left you have the noise, you reach a certain threshold, and everything in between, that's your dynamic range, according to the ISO standard. So now what I want to give a certain heads up is there can be a problem with this definition. And there's no or there are a couple of good solutions like the CDP measurement in IEEE P2020 that can help here significantly to describe these effects, but there's no other standard yet. So there's still a lot that people claim a very high dynamic range, but yeah, it's not actually the same. So what is the problem here? So in automotive, you have, in very often cases, you have multi-exposure HDR. So basically you combine multiple exposures into a single image. And for this image, you then want to define the dynamic range. And what you see here is two different configurations of the same sensor with different dynamic range configuration. One gives you 120 dB dynamic range, the other one gives you 144 dB dynamic range. And if we have a look, and what we see here is the signal to noise ratio plotted versus the illumination or the luminance in the scene. And yes, according to this SNR curve, it's true. In one case, you have the 120 dB, in the other one, you have the 144 dB. But what you also see is that we have these drops in between. So it's that is the reason. In this case, we have two drops because we have three exposures, and these drops happen when you go from one image, so from the bright part of one image to the dark part of the next image. And that's where you get noise into where you don't expect it. And we get these SNR drops. So in this, this is a little image, actual measurement image. So it's not faked. It's a real image that we captured with the automotive camera. And you see that the bright patches show significantly more noise than the dark patches. How come? That's the SNR drop. So that's something that you have to really keep in mind. So even if you have a sensor and you say this is 120 dB or has 144 dB, it does not mean that the entire range from low to bright is actually a full dynamic range, full information. You can have these drops in there that can cause trouble or can cause problem. So you have to be aware of this and yeah, specify properly, test properly your dynamic range. Okay, thank you for watching about these items regarding OVCF, noise and dynamic range. Thanks for watching and see you soon.